Okay, today, composition of mixtures. Mostly, this is just practicing, not much in the way of new material. So first kind of question, this is pretty labor-intensive question, but it is an empirical formula type of question that some people call elemental analysis. Let me make this a little bit bigger here. Okay, so we already have an answer, but how do we get to that answer? So the first thing we should do is try to figure out a chemical reaction. Organic compound, we don't know what the X, Y, and Z is for that, but it's going to be combusted. So this is a combustion reaction. All combustion reactions have to use oxygen gas, and they all make carbon dioxide, and they all make water. And it states that below. So then we don't know the organic, but we know it's something that has C, H, and O. We'll just call those X, Y, and Z because we don't know what those subscripts are. So we know that 22 grams of carbon dioxide is produced, so we can always turn grams into moles. And what we're really trying to do is find moles of carbon, moles of hydrogen, moles of oxygen. So like I said, this is a little labor intensive, but let's get started here. And to kind of make this so I can fit it all onto this little spot here, I'm not going to go 22.0, but there is a 22.0. Then I'm going to go in the periodic table and find how many moles of CO2, or how many grams of CO2 are in a mole, and it's about 44 grams. And then, you know what, let's not do a multiplication there, let's do an equals. So that equals a half. And there's one carbon in one carbon dioxide, so that also means it equals 1 mole of carbon. But let's put that together right here. 1 mole of carbon dioxide and 1 mole of carbon. You know what? Let's go and turn this back to grams. And maybe you don't know why we're going to do this yet, but it's going to become obvious in a little bit here. So there's about 12 grams of carbon in a mole of carbon. So a half times 1 divided by 1 times 12 is 6 grams of carbon. By the way, this answer I think actually has a misprint in it. We'll find that out in a few minutes. Okay, so let's do the same thing with the water. 13.5 grams of water. And let's do the exact same thing we just did there. So in 1 mole of water, there is 18 grams. That's not going to come out to be a nice number, but 13.5 divided by 18 is about 0.75 moles of water. And then let's continue on with that. Instead of finding moles of carbon to grams of carbon, let's do hydrogen. So in 1 mole of hydrogen, there is 1 gram of hydrogen. Whoops, I got ahead of myself. Grams and moles don't cancel. But yeah, we got definitely ahead of ourselves there. So in 1 mole of water, there are 2 moles of hydrogen. And then in 1 mole of hydrogen, there is 1 gram of hydrogen. The great thing about factor label is that as you're doing it, if your units aren't canceling, top and bottom, you know you're doing something incorrectly. What did I say carbon for? That's hydrogen. Okay, so 0.75 times 2 times 1 divided by all the ones is 1.5 grams of hydrogen. So that organic compound, when you burn it, all the grams of carbon come from that organic compound, and all the grams of hydrogen come from that organic compound. But the oxygen comes from, let's change this pen color. It comes from there, but it also comes from there. So we're not able to do the same exact thing to figure out how many grams of oxygen we have. But we know that there is 11.5 grams of the organic. So if you go 11.5 minus all the grams of carbon minus all the grams of hydrogen, you'll be left with the grams of oxygen. And that's going to come out to be 4 grams. So there's 4 grams of oxygen that's in that organic compound. So now that we have 4 grams of oxygen, 6 grams of carbon, 1.5 grams of hydrogen, now you are into the question that you would get in first year chem, where you have to figure out the empirical formula. So grams to moles, whichever of those moles is smallest, divide them all by that number. So let's do this. Let's move this up a little bit. Give us a little bit more room. And remember, I said there's going to be a misprint here. So let's actually just knock that out. Okay, so we had 4 grams of oxygen. So let's just write that over there because it was above. Okay, so let's do the 6 grams of carbon. And 1 mole of carbon equals 12 grams of carbon. So we have a half a mole of that. The hydrogen, 1.5 grams of hydrogen. There is 1 mole in 1 gram of hydrogen. So that's 1.5 moles of hydrogen. I'm not going to quite have enough room, so I'm going to put it over here for the oxygen. We had 4 grams of oxygen and 1 mole of oxygen. There are 16 grams of oxygen, so that's 0.25 moles. So now all we got to do is figure out which of the smallest of those, and 0.25 is the smallest, so divide everything by 0.25. One, 2, and 6. So looks like we got our empirical formula. Those are lowest whole number ratios. So 2 carbons, 6 hydrogens, and 1 oxygen. You don't have to know this yet, but you will. It would look like we'll get there. We're not quite there yet. It's going to look like that, and that is actually called ethanol, or ethyl alcohol. Okay, so that is definitely lots of labor to do that kind of question. Question number 2, no calculator. So we're gonna attempt to do this without a calculator. So let's see what we got here. So we have 4 samples, and they have different grams of material. Now, there's probably a couple different ways you could go about solving it. Yeah, we know the answer is B. So what was answer B? It looked like 72 grams of carbon and 12 grams of hydrogen. So again, you're gonna learn your own problem-solving method. There's a couple different ways you could go about doing it. You could actually go through process elimination. You could also look at the answer, and the answer looks like it's a 1:2 ratio, and figure out which one would give you a 1:2 ratio. And I think it will be B, not just because the answer is B, but 72 grams of carbon and then 1 mole of carbon, there's 12 grams. So that's going to give you 6 moles of carbon, and then 12 grams of hydrogen. 1 mole, 1 gram is 12 moles. So guess what? A 6:12 ratio is the same thing as a 1:2 ratio. So you just had to divide each of those 4 by 12. When I say that, the carbon column, and then divide all the hydrogen by 1 and see which one gave you a 1:2 ratio. Okay, moving on. Oh, another no calculator question. Okay, so again, often I won't already give you the answers here, but how do we get to the answer? So first of all, many of these questions are going to have a lot of lead up. That doesn't mean that all those words are going to be particularly important, but here is definitely, this is going to be extremely important. Why is a chemical reaction that's balanced important? Because it gives you the molar ratio of all the chemicals. And then of the chemicals, it looks like, well, it gives you a number of pieces of information, a bunch of things. But down here in the question, again, more words, it tells you how much of that chemical is produced. And then it also wants to know something about copper. So that's this chemical. So it looks like it's a ratio of 1:1, molar ratio, because there's a 1 and a 1. And if the balanced chemical equation is not given to you, you got to make one. They gave you this one because it's fairly complicated, but sometimes it may not be as complicated as this one, and so you'd have to make sure you do that yourself. So if you have 0.01 moles of copper nitrate, that means that you would have had 0.01 moles of copper. So let's start off with that. And we're trying to get to a percent. And percent is always part divided by total times 100. It gives you the sample already. That's the total. So it already gives you the 2, but we need the part. And the part they're interested in is the copper. So we're going to have to figure out what grams of copper go on top. Well, we have the moles. And on the periodic table, we have, on my periodic table, it says 63.55 grams are in 1 mole of copper. So you shouldn't need a calculator because this is a 1 right here, and all you're moving is a couple decimal places. So I think this is going to be 0.6355 grams of copper. And then this is where maybe you guys are not in really good practice doing mental math. But here is our part, 0.6355, and our total was 2 because 2 was given. and then times 100. So how many times does 2 go into 6? Goes into that 3 times. There's only one answer that has 3. And if you get to that part, that's usually going to be enough to give you your answer. So you will have to practice your mental math. I know it's been a long time since you've done mental math, but you will have to do a little bit of that. Okay, let's move on. No calculator again. Okay, so it says we already know the answer, but let's figure that out. So we have a chemical that should have just NaCl in it, but it is impure. Impure means it has something else in it. Student analyzes the sample and determines that this impure sample has 75% chlorine. So it has this chemical and then 75%, well, actually it could have a whole bunch of chemicals, but 75% of it is chlorine and the rest is something else. So when they looked at pure salt, NaCl, it only has 61% chlorine. So that means that this material has more chlorine percent-wise, mass percent-wise, than pure NaCl. So what would be able to give something a higher percent of chlorine? Well, it looks like we have some choices. We have something that has I in it. Well, if you have I in it, that's not going to give you more chlorine. That's going to give you less chlorine. So we don't like answer B. And it already says it's pure. Sorry, it's impure. So that means it can't be just NaCl. So now we're down to something that has K in it or something that has Li in it. Well, Li is lighter than Na, and it's certainly lighter than K. How do I know that? From looking at the periodic table. So if you have LiCl, that's going to have a higher percent chlorine. The KCl, because the K is heavier, is going to have a less percent of chlorine. So if we want the percentage to be higher than 61%, you're going to have something that has that going on. So something that with Li, anything that's less mass than sodium. Okay, so that's how you get to that answer. Definitely no math required on that question. Okay. Sometimes I'll take questions directly from AP tests, and that's this one here. And also we're going to have a lab that's going to have a lot to do with this kind of question. Okay, so we have a chemical reaction and it's balanced, which is really important. And it looks like we have a mixture of a compound, and the mixture has NaHCO3, that's sodium bicarbonate, and it also has Na2CO3, which is sodium carbonate. So sodium bicarbonate and sodium carbonate. Well, this chemical reaction here, you can make all of the sodium bicarbonate become sodium carbonate. So when you take this mixture, the sodium carbonate in here, nothing will happen to it, but the sodium bicarbonate will all get decomposed into sodium carbonate. So it gives you some molar masses, so you don't have to look at the periodic table to get those. Just saves you a little bit of time. It says how the student does this in the lab. So they take all the chemical. Student places a sample of that mixture of chemical into a pre-weighed test tube. So there is the mass of the test tube. That is attached to a container that holds a drying agent. Drying agents are able to take all the water that's in a compound and suck it out. And there's our water. Student heats the test tube strongly with a Bunsen burner for 10 minutes. So this reaction only happens, that's a triangle, when you add heat to it, during which time all the water produced by the reaction is captured by the drying agent. Okay, so we can figure out that number. And if we can figure out one part of the chemical reaction, we know all the other parts of the chemical reaction. So it looks like it's a 2 to 1 reaction. Okay, so if we have the test tube mixture before heating, if we subtract these two numbers, that would give you the mixture, right? And then what else? If we have the drying agent and the drying agent with the water, if we subtract those two, that would give us the amount of water. So part A, calculate the number of moles of sodium bicarbonate present in the mixture before the reaction was initiated. So instead of me doing the work, I already plucked out all the worked out answers, and we can kind of go back and forth. So let's check out A. There it is. Okay, so they took, let's go back to they took these two drying agent amounts. This is the drying agent with the water, and this is the drying agent before you started. If you subtract those two, that gives you the mass of water. And then we converted grams of water to moles of water. And then there in the balanced chemical equation was a 2 to 1 ratio. So we then converted it into moles of sodium bicarbonate. So there is the sodium bicarbonate moles that we originally were present with. So one nice thing about these answers that they give you is they tell you how they grade them. So if you were able to figure out the grams of water, you got a point. And this is the way the tests will be also, that you do some work, and if you get if you do it right, then you get a point. If you do something else right, you get another point. By the way, if you would somehow screw that up and you get the wrong answer, but you use that wrong answer correctly in this part, you can still get that point. So no, your answer won't be 0.0188. It'll be some other number. But if you use your wrong work correctly, you can still get partial credit somewhere else. So you can still get this point again. Okay. So often we'll have to use B to do C. Not always, but sometimes you have to use C to do D. Okay, so it looks like we are going to do that. So let's go back to our original question. Determine the mass percent. So again, I had said that mass percent is always part divided by total times 100. Okay. So let's figure that out. Let's go and see what we got and where these numbers are coming from. So we already have our part. Okay, and well, we almost have our part. Mass percent is mass of part divided by mass of total. So we did have to convert this into grams. And how do we do that? With the molar mass, and that molar mass was already given to us. Okay, so 1.58 is our part. And how do we find our total? The total is all of the mixture. And so if you remember, we weighed out a test tube. And then we weighed out the mixture and the test tube. So if you subtracted those two numbers, that's going to give you all of our mixture. And it should be, there we go. So 17.648 minus 15.825 is our total mixture amount. So divide those two times 100, and there is our percent. Okay, so again, if you do this correct and use it correctly here, you get a point. If you would somehow screw that up, but you use it correctly down here, you can still get that point. Okay, so now I think the hardest thing to do is these kind of questions. And let's go back and look at the original question. If a student spills some of the mixture out after initial weighing, how would this error affect the mass percent calculations? And you have to come up with some reasoning as to why that would happen. So the best way to do it is to look at all of your math and see where that number would be impacted. And so let's go and look at the work. Well, let's look at their answer first. It said it would be smaller. So let's and let's try to figure out why it would be smaller. Whoops, yeah, let's go back down to there. So if you lost some of your mixture, I think it's going to make, it's going to make this a less of a number. So you would have been losing some of that. So instead of 15.825, it would have been a smaller number. And if you would have made this a smaller number, when you subtracted it from 17.648, you would have gotten a bigger number at the bottom of that fraction. So you might have gotten something like 1.58 divided by, instead of 7, well, it's still, well, let's go. I don't know. Who knows how much you would have been spilling, but you would have gotten a number that would have been bigger down here, which would then have made this percent go down. And we'll definitely have to practice those kind of things a lot more, and we'll do that in the lab also. And I think that might be it. That was our last question. Yeah. Okay.